Okay, now that you're good with IJs and Ks, um, it's time to begin a little look at an electrostatics electricity preview for most of you, review for maybe one of you. Okay? And the reason we're doing this is because when we get to magnetism, I will refer back to how it compares to electricity. And there's some things in electricity that we actually need to use in magnetism. So we need to have a little basis here. But the other interesting thing is the parallels. And it's not just a parallel between magnetism and electricity, there's also a parallel with gravity. So we're going to look at first, even though this says a preview of electricity and electrostatics, I'm going to look at gravity and like what's called gravitational fields, even though fields. So just a couple of minutes on this. Okay, I think you all know what gravity is. I think you all know that if this is our Earth, then there's an area around the Earth where any object that enters into this area that has mass is going to experience a pull towards the center of the Earth. And that pull is known as the gravitational force. It pulls it down. And this area around the Earth is known as the gravitational field. Not a field like where a little deer is out eating wildflowers, but when we in physics, when we talk about a field, it's the area around an object where if another object with a certain property enters into that area, it's going to experience a force. And the certain property for gravity is it has to have a mass. So this is the gravitational field, and it's experiencing a force. Now, if you had me for grade 11 physics, then I would have shown you the big equation for gravitational force. It's G m1 m2 over r squared. If you had me as opposed to another teacher, then you would remember that we talked about this equation where m1 and m2 are the masses of the two objects. Of course, in kilograms, right? So if this is the Earth and this is, space station or something, it'd be those two masses. R is the distance from the center of one to the center of the other. Measured in meters. And the Fg is a universal gravitational constant. This equation is known as Newton's universal law of gravitation, and we will come back to it in physics 12 when we get to the planet unit, okay? But what Newton told us was that this equation doesn't just work for the Earth. Sorry, I just need to balance that better because it's moving. Doesn't just work for the Earth pulling on objects. Every object in the universe has a gravitational field around itself, including you and I. So we all have a gravitational field around ourselves, and if another object with mass enters into that field, they're going to experience a force inward. Okay, a gravitational force of attraction, we would say. But if you think about it, our masses are really tiny. And so, and this universal constant, G, is equal to 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. So if you put my mass and your mass in there in kilograms, so let's say like 60 and 80 kilograms, and multiply it by something times 10 to the negative 11, even if we're just a meter apart, this force is going to be really tiny. And indeed, this force is so tiny that although we're putting a gravitational force of attraction on everybody around us, none of us are even aware of it because it's so small. We're not able to detect it. But if we trade one of our masses in for the mass of the Earth, then everything changes. Then, because the mass of the Earth is 5.98 times 10 to the 24th kilograms, compared to a person's mass, which might be like 80 kilograms. And for some of you, that's a lot. Okay? Obviously, if we exchange one of those m's of the 80 kilograms for the 5.98 to the 24th, it's going to significantly change the size of the force. Maybe just so you get a sense of it, let's do an example. So first, let's say mass 1 is 80 kilograms, mass 2 is 60 kilograms, and let's say you're 2 meters apart. So if you do Fg is equal to G m1 m2 over r squared, it'll be 6.673 to the negative 11 Newton meter squared per kilogram squared times 80 kilograms times 60 kilograms divided by 2 meters squared. So just take a second and punch this in your calculator. 673 to the negative 11 times 80 times 60 divided by 4. And when you do that, you get 8.0076 times 10 to the negative 8 newtons. Obviously, this is so tiny we wouldn't be able to feel it, and that's for two people only 2 meters apart. I'm putting a gravitational force of attraction on any and every other object in the universe. So right now, even though we're in our separate buildings, I'm putting a gravitational force of attraction on you. We are definitely further apart than 2 meters, so that force is definitely smaller than this, but I'm still doing it. So now if we trade one of us in for the Earth, so let's keep our 80 kilograms, and let's say the second object is the Earth now, 5.98 to the 24th, and if we're standing at or near the surface of the Earth, the radius of the Earth, 6.13, I think it is. 6.38 times 10 to the 6 meters. I think that's right. Okay, so even though we might be in my classroom, we'd be a few meters above the surface of the Earth, it's not going to make a difference when we're talking 6 million. And so now we do Fg is equal to G m1 m2 over r squared. So 6.673 to the negative 11 Newton meters squared per kilogram squared. We keep the 80 kilograms. We do 5.98 times 10 to the 24th kilograms. And on the bottom, 6.38 times 10 to the 6 meters. Don't forget to square it. Okay, so plug this into your calculator. 6.673 to the negative 11 times 5.98 to the 24th times 80 divided by 6.38 to the 6th squared, and you get 784.28 newtons. Definitely significantly bigger than the times 10 to the negative 8. This we can feel. This actually is big enough to cause us to move. This is why if you step off your bed, you fall towards the Earth, because the Earth is putting this force on you. Now, if we did it for each other, the only thing that would change would be this 80 newtons, right? If we're all at or near the surface of the Earth, the universal gravitational constant, which is the same everywhere in the universe, thus its name, the mass of the Earth, and if we're at or near the surface of the Earth, the radius are not going to change. So we could find the pull on each of us by just switching out the 80 kilograms. So after